Coming back?
I know I wrote it.
Okay. All right. So that was really fast. What are the stories behind that? All right. Last concept, ladies and gentlemen. Last concept in electron configurations is the idea of an ion. An ion configuration. So you know that the electron configuration represents how the electrons are ordered around the atom. 1s2, 2s2. When you hear 2p6, that means there's 6 electrons in the p orbitals in the second level, 2p6. Okay. Now, when you add electrons, pretty simple. You just add one number to the electron configuration. Add one number to the electron configuration, and you have the negative ion. Now, first of all, we need to remember or remind ourselves that atoms are normally neutral when there's same number of protons and electrons. However, atoms can be ions. Ions have a different number of electrons. What is the charge of an electron? Negative. Charge of an electron is negative. So, if you add an electron to a neutral atom, that atom becomes negative. 0 plus -1 equals -1. 0 plus -2 equals -2. On the other hand, if you take away an electron from a neutral atom, that atom becomes positive. 0, even the football players can do this one. 0 minus -1 equals +1, right? 0 minus -2 equals +2. Good. So, yeah. So, consider the sulfur. Sulfur's configuration is neon 3s2, 3p4. Okay? Sulfur's configuration is neon 3s2, 3p4. So, if you found sulfur on the periodic table, right under oxygen, and my laser is, there it is. If you found sulfur on the periodic table right under oxygen, there it is. There we go. Then there's still some space for 2 more electrons. Okay? That shell, that level can still hold 2 more electrons. So, what if sulfur gained 2 electrons? What would its electron configuration become? 3p6, yeah. So the sulfur 2- ion has the configuration neon 3s2, 3p6. Sulfur then looks like a noble gas. It looks a lot like argon. Okay? So other atoms that are passing by don't see a sulfur atom anymore. They see an ion that looks a lot like argon. Like, hey, you got a 3p6. You look kind of like argon. And sulfur's like, I know. I got 2 more electrons. So 3p4 became 3p6. This affords the ion a special stability. Okay? Listen carefully. Atoms want to look like noble gases. Atoms that look like noble gases have a special kind of stability. It's called, by the way, I know this is probably going to blow you away, noble gas stability. Whoa. Yeah. Atoms want to get noble gas stability. If you're an atom, that's your goal. You want to look like a noble gas. Because noble gases are the best of the best. So, give me a thumbs up if this is resonating with you. You kind of get this idea. All right. Wave your hand around if you have a question. None. Okay. Now let's take a look at this. Calcium. Calcium has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Calcium has 2 electrons hanging out in the 4th shell, and only 2. There's only 2 electrons in the 4th level. What would calcium's configuration be if it lost them? What would calcium's configuration be if it lost those 2 outer electrons? That's you. Yeah, 3p6. So we would say the calcium 2+ ion is 1s2, 2s2, 2p6, 3p6. And take a look at this. Calcium also looks like argon. Calcium 2+ ion looks like argon, just like the sulfur 2- ion looks like argon. Because the protons make up the atom. The electrons give it its properties, but the protons give it the ion. then you know what's going to happen? That sulfur that's cruising along with a -2 charge, and that calcium is cruising along with a +2 charge, if they see each other, guess what they're going to do? They're going to stick. Because opposites attract. +2, -2, they're going to stick. Opposites attract. A charge. Okay, does this idea make sense?
Yeah, but I'm not.
Okay. So in summary, when you have an ion and you add electrons, you just add them in filling order. You add one to nitrogen, it's going to look like oxygen. You add another to oxygen, it's going to look like fluorine. You're going to add one to fluorine, it's going to look like neon. Okay? When you add electrons, you add them in filling order. But there is a wrinkle. And the wrinkle is this. When you remove electrons, you remove them from the highest shell first. When you remove electrons, you remove them from the highest shell first. Why is that important?
Isn't that the opposite of the other one?
Well, in many cases, you can just undo the electron configuration, just wind it backwards, but not all of them. For instance, iron. Iron is Fe. Iron has the configuration argon 4s2 3d6. That was on your quiz yesterday?
Yes.
Okay. That's iron's configuration. If you take away 2 electrons from iron to make iron 2+, it will have the configuration argon 3d6.
Why not for us too?
Oh, because
Who can answer that? Why not 4s2?
Because for us, there's a higher energy level than 3D6.
Because why?
Exactly. 4s2 is a higher energy level in so much as the 4s2 is further away from the nucleus than the 3d. Now we know that the 4s2 is lower in energy than the 3d, and Cameron's texting his girlfriend right now about it, or boyfriend. I don't want to judge. So we know that the 3d is lower or higher in energy than the 4s. But if we're going to take away an electron, we don't take away an electron, other atoms do. So when another atom floats by iron, it's going to see the outer electrons first, and those are the ones it's going to take. Does that make sense? So the 4s, further away from the nucleus, so you always take away the 4 before you take away a 3. Always take away a 5 before you take a 4. Does that make sense?
Yeah.
All right. Any questions before we move on to the very last thing?
Wait, I have a question.
Yes.
So, like, there's two, let's say the Fe2 plus, 2 positive, and then there's no FS2, or
4s2.
4S2.
Because the 4s2.
Is that only because there's 4S2 and 2 is also there?
Yes.
Okay.
The 4s2 electrons have been lost, creating the +2 ion.
Okay.
The +2 means I lost 2 electrons. Really, iron? What 2 electrons did you lose? My 4s's.
And how do they know it's 4S? Because there's 2 on the end and you take all the way over there.
Yep.
I'm hearing that.
All right. Next thing. Octets. Pokemon. So I know some of you guys play Pokemon, and some of you play Digimon, and some of you play Magic the Gathering, and some of you play Hearthstone, and those other crazy games. So there's this new card game that comes out. It's Awesome Mon. And Awesome Mon has 100 cards in its complete set. So you go to Target and you buy those Awesome Mon cards, and you've got 98 of the 100 cards. And you go to an Awesome Mon convention. What are you going to try to do with the Awesome Mon convention?
Get the 2 cards.
You're going to try to get the 2 cards you don't have, right? Because you're almost to a full set. You're going to try really hard to get those last 2 cards. On the other hand, you're going to find someone who's been playing Awesome Mon a little bit longer, and she's got 103 cards. Is she going to worry that much about those extra 3 cards? No. Now, she's not going to throw them away, because they're still Awesome Mon cards, but she's not going to hold on to those 3 cards very, very tightly. She'd be like, yeah, I'll trade my 3 cards for a sandwich. Sure, why not? Because she's got her full set. That's how atoms work. If atoms have a full set of electrons, they work really hard to keep their full set. If they've almost got a full set, they're going to work really, really hard to get that last electron. And if they've got a full set plus 1 or 2, they don't care that much about that 1 or 2. They're not going to give it up just like, they're not going to throw it away, but they're not going to hold on to it very strongly. Does this idea make sense?
Yeah.
Now the full set of electrons is called an octet. An octet is 2 electrons in the s and 6 electrons in the p. The octet are the 8 valence electrons. Valence electrons are the electrons in the highest s and p shells. So the electrons in the highest s and p shells are the valence electrons, and an octet is 8 of them. Totally filling up your s and your p gives you an octet.
So an octet is 8 valence electrons?
Correct. Exactly that. An octet is 8 valence electrons. So neon has an octet in what level? Level 2, yeah. So neon has an octet in level 2. Argon has an octet in what level? Level 3. So neon has noble gas stability because it has an octet in level 2. Argon has noble gas stability because it has an octet in level 3. Make sense? All right, cool. So if you have 7 electrons, what do you spend most of your time doing?
Trying to find the 8.
Trying to find the 8th, exactly. And if you've got an octet plus 1, do you care that much about that last one?
No.
No. So if chlorine, right there, how many valence electrons does chlorine have?
7.
This is really important. Super important. Chlorine has 7. 2 from the S and 5 from the P. So if you have chlorine, if you're chlorine, you've got 7 valence electrons. You're going to try really hard to get that last one. With 7 valence electrons, you are highly unstable.
Oh.
But with 8 valence electrons, you are totally chill. Very stable.
So those are all really stable.
Yeah.
Those aren't.
Correct. Now on the other end of the periodic table, we have sodium. Here's sodium. Sodium has an octet in level 2 plus 1 electron in level 3. Does sodium really care about that 1 electron?
No.
No. If you put sodium in water, it goes bang! Because that last electron is trying to be taken by the water molecules. Okay? So sodium doesn't hold on to that last electron very strongly. I'll show you that in a few months. I'll show you when sodium goes, you basically put it in water and it goes fizzle, 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 bang! Lithium goes fizzle, fizzle, fire. Because it also has an extra electron. And potassium doesn't even wait for the fizzle. It just goes bang. And rubidium and cesium, they go bang before they even reach the water. They go bang with the water right above it. Okay, rows 1 then rows 2.
So the chlorine and all that, the bromine, whatever, iodine, all of them are like the least or the most unstable out of all of them.
Mhm.
And then it just goes like this from there.
Yes. In fact, that is the entire next unit is called periodic trends. And it's trends about how atoms do what based on where they are on the periodic table. So yeah, your most unstable atom, your most vicious atom is fluorine. How many valence electrons does fluorine have?
7.
7. What does it spend all of its time doing?
Trying to get the 8th.
Trying to get the 8th. Okay. If this makes, okay, one more.
I'm confused on how you got the sodium.
Okay, so sodium has 1 valence electron in its 3s1. Just 1.
Oh.
So sodium has an octet in level 2 up here, and then it's got 1 spare. Now, it doesn't hold on to that spare very strongly.
Oh.
So when a water molecule comes along, it's like, can I have that spare? Sodium's like, yeah, please take it, just take it, just take it. And then that's why it reacts so violently. Okay, does that make sense?
Yeah.
Okay, if this is resonating between your ears, give me a thumbs up. If you want to talk about it again, wave your hand around. All right. So, yeah, pretty soon. Follow the little green dot, because this is critical. Good question.
Wait, okay, I have one more question. So the lithium so lithium all the way to the neon is 8, and then Na, what is that called again? Sodium.
Sodium?
has an extra one?
Yes. So
So it already
okay.
has 8?
I think I'm going to answer this in just a second. Lithium down. These all have one valence electron. These are all S1. Beryllium down has 2 valence electrons because these are all S2. Boron down are S2, P1. How many valence electrons does boron's group have?
3?
3. Carbon's group, S2, P2. How many valence electrons does carbon's group have? 4. Nitrogen?
5.
Oxygen's group?
6.
Fluorine's group?
7.
Neon's group?
8.
Okay, so let's do that again. So if you don't like speaking out, if you like speaking in class, now's your chance. Okay, so valence electrons. Lithium's has how many?
1.
Berylliums?
2.
Borons?
3.
Carbons?
4.
Nitrogens?
5.
Oxygens?
6.
Fluorines?
7.
Okay, so, and then neons has 8. So, if fluorines has 7, what charge will it have when it is stable?
1. More.
Negative 1. So remember, electrons are negative, so fluorine wants 1 more electron. So the charge fluorine will have when it is stable is negative 1. Oh, because, exactly. Lithium's group. Lithium's has 1 valence electron. What charge will lithium's group have when it gets rid of that electron? Positive 1. Does this make sense to you? Can you see it in your mind's eye? Okay. Beryllium's group will be what? Plus 2. Boron's group?
+3.
Plus 3. Fluorine's group? Negative 1. Oxygen's group? Neon's group? 0. Carbon's group? Okay. Carbon's group has 4 valence electrons. What makes carbon so cool, and the reason you and I are called carbon-based life forms, is carbon can gain 4, or it can lose the 4 it has. And one molecule might gain 4, and the one right next to it might lose 4. Carbon is really cool because it is equally likely to gain 4 or lose 4, making it very, very versatile. Thank you. Okay, so if you've got 6, you really want to get 2 more. Oxygen, sulfur, selenium, they got 6. What charge will they have when they are stable? Negative 2. How do they become negative 2? By gaining 2 more. Nitrogen's group. Nitrogen's group has 5 valence electrons. What does it want to do? Gain 3 more. How does it gain 3 more? Or what charge does it get when it gets 3 more? Negative 3. So this is the pattern. 1, 2, 3, 4, 5, 6, 7, 8. Plus 1, plus 2, plus 3, plus or minus 4, negative 3, negative 2, negative 1, zilch. Okay.
So it does go like this.
Yes.
Yeah, I said that. I'm so smart.
All right. Questions before I turn you loose on your worksheet?
This kind of reminds me of Pascal Charles.
Katie, can you press the button, please?
Yeah.
All right. On the back.